Hello friends, welcome. Today we would be continuing our series of lectures on speed. However, today we would specifically concentrate on problems where the surface on which the objects are situated is itself moving. Right? So this object, maybe it's a boat, it is moving, and the stream in which this boat is located is itself moving, and we'll understand how to solve such problems. So before we start, like every speed class, you have to be conversant with this formula. Speed is equal to distance over time. It is very important. And second thing, like I say in every class, you have to be very familiar with ratios which come from this formula. So for example, if distance is constant, this formula tells us that speed is inversely proportional to time, which means if I increase the speed, my time would decrease and vice versa. So with that background, right, with that information in our head, we can now start with the problems related to boats and streams. And of course, these problems are special because the streams on which the boats are located, not only the boats are moving, but also the stream on which these boats are playing is itself moving. So the stream is moving, and on top of it, boat is also moving. So here is our friend, Mr. Balloon. He has come here to help us understand this concept. So Mr. Balloon has a serious problem, and what is his problem? His problem is that he runs on this treadmill. Treadmill, if you have gone to a gym, you would have seen this machine. It's a machine in which there is a belt, and this belt, when the person runs on it, the belt moves in the opposite direction. So the person is running this way, the belt is moving in opposite direction. So there is a person, another person, an observer, a person who is seeing all this drama unfold. So this Mr. Observer tells Mr. Balloon that, look, you are running on this treadmill, right? You think you are running on this treadmill, but from my perspective, the way I see it, you always appear stationary. Which is correct, right? Because this person, as we can also see, is always standing here. Whether he is running or not running, he is always standing at the same location with respect to ground, right? That is the concept here. The ground, with respect to ground, with respect to the floor of the gym, this person is always standing here. And this Mr. Observer just tells him that. Mr. Balloon tells him that no, when the treadmill is running, I am running. Okay, so I am running in this direction, right? How can you? So you are wrong. So what is the dilemma here? What is the basic problem here? The problem is, of course, of perspective. The problem is of relative speed. This particular relative speed is different from what we have discussed so far, because the surface, the treadmill on which Mr. Balloon is running, it's itself moving in opposite direction. It is cancelling all the speed of Mr. Balloon. So Mr. Balloon runs in this direction, let's say at the rate of 3 meters per second, but the treadmill moves in opposite direction at the rate of 3 meters per second, and to Mr. Observer who is sitting on the ground, it looks like Mr. Balloon is not moving at all. Right? So this person on the treadmill, it appears, although he is running, it appears that he is not moving at all. And so with that basic information, with the picture of this treadmill, right, this belt and the person running on the belt in our head, now we would really understand how we can apply this same concept to boats and stream problems. So let's get started. I have a small demo here which would illustrate this concept very easily. Right? It's a very simple concept, and I recommend that you definitely 100% attempt these problems. After this class, you will understand this concept. The maths in these problems is very simple, as we will see later, and these are very scoring questions. Without much work, you will be able to solve them. So here I have again an observer who is sitting on the shore, and then there is this, imagine this yellow colored block, right? It is our river, it is moving in this direction, and then there is a boat. This is blue colored boat, right? So now if you look at it, this boat and the observer start at the same position, they are in the same straight line. In 1 second, let's say the boat moves forward by 1 meter. So the speed is 1 meter per second. So this observer, if this water is stationary, it is not moving at all, then this observer would correctly see that the boat would say that I am moving at 1 meter per second, the observer would also say that that you are moving at 1 meter per second, and there is no issue. But let us say that in this time that the boat moved by 1 meter per second, the stream itself moves by 2 meters per second. So now from the point of view of observer who is standing on the shore, the boat has moved not only this 1 meter but also this 2 meter moved by the stream, and hence the relative speed of the boat with respect to this observer becomes, right. So we call this speed downstream, because the boat is moving down the stream in the direction of stream. We call this the speed downstream is equal to not only the speed of the boat but also the stream has moved. So his stream has really helped the boat move another 2 meters. So this is the speed downstream. You have to remember this formula. Similarly, now the stream, let us say, moves again in the same direction, in this direction. So the stream moves in this direction, but the boat, let us say, moves in this direction. Right? So the boat in 1 meter moves, let us say, 3 meters per second. So it has come here, but in the meanwhile the stream has moved back, right. It would appear to the boat that the stream is moving back, it moves in that direction by 1 meter. Then stream has cancelled from this point of view of this observer, from those 3 meters that the boat has moved, stream has cancelled some of the work. It has cancelled, let us say the speed of the stream is 1 meter, it has cancelled, it has taken away from those 3 meter 1 meter, and hence speed of the boat upstream means when the stream is moving in the direction opposite, the boat is moving in the direction opposite to that of stream, it is moving against the stream, that is upstream. Okay. So in that case the stream cancels some of the work done by the boat, and hence the upstream speed is the stream of the boat minus the speed of the boat minus the stream of the current. This is the speed of the current or speed of the stream. And downstream speed, of course the current helps the boat, and the downstream speed becomes the sum of the two. So those two basic formulas you have to remember, right. And there are two terms also, right, we just introduced. We said downstream and we said upstream. So the upstream is very similar to uphill. If you are going uphill on a bicycle, you have to do more work. Similarly, like some of the work, so like you have to do more work. Similarly, a boat upstream has to do more work because the stream cancels some of the work. So upstream, you can remember by this that the actual speed of the stream is reduced. Similarly, for downstream case, the stream, when we are cycling, if you are going downhill, the hill is helping us move. Similarly, in downstream case, right, so it's downhill and downstream is similar, you can remember it that way. Downstream, the stream is helping the boat, right. So this is an addition, and upstream case is similar to uphill, where the hill, in this case the stream, is actually destroying some of the work done by the boat. So with that information, the boat and the stream questions, we have learned that all the terminology. So this is all the terminology you need to remember. However, very often nowadays in questions I am seeing people are also asking plane question, right. So the case of plane is very similar, right. So this is a plane and this is the wind, this is the air in which it is moving, right? The case is very similar to the boat case. It's not very different, right. Conceptually it's not different at all, it's exactly same, but the terminology is a bit different. So in case of a plane which is moving in this direction, if the wind is opposing this plane, we call it headwind, because it is hitting the head of the plane. If this wind is moving in this direction, it is pushing the tail of the plane, it is known as tailwind. Tailwind case is same as the downstream case, because the wind is assisting the plane, in this case not the boat but the plane, and headwind case is similar to this case where the stream or the wind is opposing the plane. So again 4 terminologies and 2 formulas. There are 2 other formulas which we can derive from these, right. So if you look at these 2 formulas and let us say we add these. So what we will get is SD, speed downstream, plus speed upstream, we are adding this, is equal to 2SB, or speed of the boat is the average, it is the average of the speed downstream and speed upstream. So that is another formula which you, if you want, you can remember. If you don't want, you don't have to remember it, you can simply derive it, it wouldn't take long. Second thing which we can come up from here is if we subtract this equation from that equation. Subtract means that we change the sign and then add. So this SC and SC becomes 2SC, and then SB and SB cancel out, and here we are left with stream downstream minus stream upstream. These 2 can come here, right. So this is another formula. So these are the 4 formulas which you have to, if you want, you can remember these 2 formulas. These 2 formulas are absolute must, either you can understand them or remember them however you want. And then there are 4 terms: downstream, upstream, tailwind, headwind. You have to remember those. So with that basic information, let's start solving some problems. As you will understand, the problems here in these questions are very simple. They are not difficult provided you understand the concepts, and that is why examiners really are liking these problems. These are becoming very common in all exams. So there is a boat which is traveling at the speed of 13 km per hour in still water. So the water is still, the boat is flying at the rate of 13 km per hour. Now if the speed of the stream, this stream runs at the rate of 4 km per hour, then we have to find the time taken by the boat to cover 68 km downstream. Right? So the first thing that you notice here is downstream. We already know that speed downstream is sum of the speed of the boat plus the speed of the stream. So this becomes 17. We also know from our previous classes that the time is distance over speed. So the time taken becomes 68 over 17, which is equal to 4 hours. Right? Very simple, not difficult at all. And these are real exam problems. They have appeared in the exam. So it is, these are not really simple. I mean, they are indeed simple problems. Here we have a swimmer whose speed downstream is 16 km per hour. The current runs at the rate of 3 km per hour. Therefore, in this downstream speed, in this 16 km per hour, how much has the current contributed? The current is contributing 3 km per hour. Therefore, the real speed of the boat is how much? 16 minus 3, very good. So it is 13 km per hour. Good. So we know that much. And now we have to find the speed against the current, which means upstream speed. So we have to find upstream speed. We already know that it is SB minus SC, which is equal to 13 minus 3, which is equal to 10 km per hour. Again, very simple, right? Very simple problem. Moving on, a boat covers 36 km downstream, right? So here we are given 2 speeds, both the upstream and downstream speeds. We are given that. Right? So how do you find that out? The distance is constant, but the distance is changing, but the time remains constant. So both the cases, he is saying that the boat is taking 6 hours. The distance covered in both the cases is different, but of course, from our basic principle, from our formula, we can arrive at the time. We can arrive at the speed. So speed, if we know, is distance over time. So speed upstream becomes, the upstream distance is 12 kilometers, by time is 6 hours, so it is 2 km per hour. Speed downstream becomes 36 km, it is again covering in 6 hours, so it becomes 6 km per hour. What is the velocity of the current? We have to find SC. Right? Either you can go by the first principles, you don't have to remember this formula, right? So this SU and SD, right? Upstream speed is speed of the boat minus speed of the current. Speed downstream is speed of the boat plus stream of the current. So you can subtract these equations and direct get SC, or we remember the SC formula, it is SD minus SU divided by 2, SD is 6 minus 2 divided by 2, which is equal to 2 km per hour. So, speed of the current is 2 km per hour. Again, very simple. If you remember the formula, it is one line. If you don't remember the formula, then also it wouldn't take long, right? I mean, you don't have to remember the formula, provided you understand the concepts. A man can row 18 km per hour in still water. Now we are being told that 18 km per hour he can row in still water. So that still water speed is the speed of the boat. Right? So that is the speed at which the boat would move. It takes him thrice as long to row up as to row down the river. So this thrice as long is the time taken. Right? If the time taken is thrice as long, speed is 1/3. Correct. So his upstream speed is 1/3 his downstream speed. Right? So this is 1/3 downstream speed. So that is what this is telling us. It is also telling us that the speed of the boat is 18 km per hour. Now all we have to do is substitute the values. It is very simple. Upstream speed is SB minus SC is equal to 1/3 SB plus SC. We know what SB is. It is 18 minus SC is equal to 1/3. SB is 18 plus SC. If you solve this equation, SC would come out to be 9 km per hour. Again, extremely simple, not very difficult. Now we have another problem. This time I have included a problem of plane, right? So again, like I said, these are also becoming common in exams, and in case of planes, the terminology used is headwind and tailwind. So tailwind pushes the tail and therefore it is helping the airplane, and headwind pushes the head of the plane and therefore it is making it more difficult for the plane to fly. So now what we are being told here is that there is a plane flying with a headwind, against the wind it is flying, and it takes 3 hours. So speed upstream becomes 600 miles and it takes here 3 hours. So speed upstream becomes 200 miles per hour. Speed downstream is, again the distance is same, 600 miles, but it is taking it how long? Only 2 hours, less time, right? Of course, that we would expect, because the plane is being held or the wind is helping the plane. So this becomes 300 mile per hour. Right? Remember the units, it is miles. Therefore, we know that the speed of the wind, again we can apply our formula, is SD minus SU divided by 2. If you substitute the values, it will be 300 minus 200 divided by 2, or 50 mile per hour. Very simple. Right? So this is mile, not meters. I should probably write it fully so as to not confuse you. So this is miles per hour. Okay. Good. So now we have another problem. Again, in this problem we are being asked the speed of the boat with respect to the current. So we are a ratio of the speed of the boat and the current. We are not being asked the absolute values. I mean, if you notice that the problem itself doesn't give us enough data to find the absolute values. What it tells us is the upstream, the boat takes 8 hours to cover a certain distance, while it takes 4 hours to cover the same distance running downstream. So time taken while going downstream is half, right? Half, 8 by 4, it is half. The time taken to go downstream is half the time taken to go upstream. Therefore, downstream speed is twice that of the upstream speed. Right? So very important concept, right? These ratios, you have to be very familiar with this. You should be able to quickly apply the ratios. So of course, now all we are left with to do is to substitute the formulas. This is SB plus SC is equal to twice SB minus SC. So if you solve this, you will get SB is equal to 3 SC. You have to bring SC to this side. So SB by SC is equal to 3, or the ratio of their speeds is 3:1. Very simple, not difficult. Now moving on to the next problem. Rahul, there is a person Rahul who is rowing the boat here. and he is going downstream in time in 6 hours less, right? As soon as you hear the keyword less, you have to understand that it is a difference question. So there are 2 times involved, and we are given the difference between those 2 times, and the times are time upstream minus the time downstream, and their difference is 6. That is what the question is telling us. So he takes 6 hours less to go downstream. So therefore upstream minus downstream is 6 hours. So this is 6 hours. Of course, the distance we know is 12. So distance is given, and we know time is distance by speed. So it becomes 12 divided by SU minus 12 divided by SD. The downstream speed is 6. That much we know. Now I can substitute the value of SU. I know SU upstream speed is speed of the boat minus speed of the current minus 12. Downstream speed is speed of boat plus speed of current. So downstream plus comes, upstream minus comes, and this is 6. So that is about our first equation. That is the first equation. The equation from the first scenario. The second scenario is telling us that if he were, everything else remains unchanged, the distance remains unchanged. If he were to double his rowing speed, so when he doubles his rowing speed, only SB changes. He is doing nothing to change the speed of the current. That is not in his hands. He is only going twice as fast in his boat. So if he goes twice as fast in his boat, then this becomes 2SB minus SC, and of course this remains 12, 2SB minus SC, and this changes from 6 hours to only 1 hour, right? The difference in time changes to only 1 hour. So these are the 2 equations we have, and there are the 2 variables SB and SC. So if you were to simplify the first equation, you would get 4SC plus SC square is equal to SB square. That is what would come from the first equation. The second equation would give you 24SC square plus 4SC square is equal to 4SB, not 4SC square, only SC square is equal to 4SB. So substitute 24SC plus SC square is equal to 4. This SB I can substitute from here. This becomes 4SC plus SC square. Now SC cancels out, right? One SC I can remove from everywhere, and therefore my final speed of the current, if I were to solve this, would come out to be 8/3, and of course this is all in miles, so miles per hour, right? Again, not very difficult, right? If you look at it, nowhere complex maths got involved, not even a quadratic equation, right? We thought that for 1 second there would be a quadratic equation here, but that there wasn't. So again, very simple question, provided that your concepts are clear. Now moving on, here is something I wanted to discuss, because again I saw this problem in one of the exams last year. So the key here is that it is the concept is very similar, but the trick is a slight trick to it. So here we have been saying that the stream is moving in this direction, and either the boat is moving against the stream or in the direction of the stream. So boat is moving and the stream is moving, they are sort of parallel to each other. But in these kind of questions, what is happening is, imagine the stream moving in this direction, right? So stream is moving away from the camera in this direction, it's moving towards me, but the boat is still moving in this direction. So both are going perpendicular to each other, and these problems are becoming very common nowadays. So what happens, imagine again our treadmill thing, right? This entire stream is like a giant treadmill. So this entire platform is, let's say, moving in this direction. This black colored thing, it is a stream, but it is moving in this direction. It is a giant treadmill, it is a giant platform moving in that direction. If it is still, then the boat would simply cross. It is a lake, then the boat would simply cross. But if this were to happen in a river, with the river going in that direction, the boat will go straight because of its own speed. The boat always thinks that it is going straight, but the entire thing underneath, the entire platform, the stream shifts. It moves slowly and gradually in this direction, and therefore the net motion of the boat comes out to be like this. It is at an angle, it is not perpendicular, right? Because the stream has shifted the position of the boat. Right? This particular distance is directly related to the speed of the stream. Boat does not contribute in this direction. Its speed does not contribute to this distance. This distance is wholly and solely it comes from the speed of the stream. This distance the stream does not contribute, it does not help. This distance is entirely covered by the speed of the boat. So remember that, okay. Now with that information, let's solve an example based on that problem, based on this concept. When the boat is moving perpendicular to the direction of the stream, it is moving at 90 degrees. So there is a ship 4 kilometers away from the shore. So of course there is a ship right here, it is 4 kilometers away from the shore, and this is of course a river. So this stream is itself moving in that direction at the rate of 1 kilometer per hour. Now unfortunately this particular boat, our boat, has developed a leak. So there is a leak, there is water seeping in. The water seeps at the rate of 15 tons of water in 1 hour, but there are pumps which can throw out 9 tons of this water. So 9 tons of water, 12 tons of this water per hour can be thrown by the pump. So every hour how much water is in net gained by the ship? 15 minus 12, 15 comes in, 12 goes out. So 3 tons of water is left in the ship every hour. 9 tons of water would sink it. So in 1 hour the ship accumulates 3 tons of water. It will accumulate 9 tons in 3 hours. Right? So that much we can understand. So the ship in net, right, that's what the question is saying, has total of 3 hours to go from here to here. Now in those 3 hours, while the ship is trying to go, right, of course it is sinking, so it would not take a detour, right? I'm the ship's captain, I want to reach the shore as fast as possible, so I won't go like this, I will go straight to the shore, right, perpendicular. So the ship will try to move perpendicular in this direction, and in 3 hours it would sink, but in those 3 hours the stream would move this boat in this direction. And how much would the stream move? It would move 1 kilometer, it moves in 1 hour. So in 3 hours it would move 3 kilometers. We are being asked, what is this distance? What is the real distance covered by this boat? So instead of going like this, which it wanted to go, it actually went like this, and therefore its trajectory is slightly tilted. Not the 4 kilometer per hour, but it would have traveled this distance. And this distance, if you notice, this is a right angle, this is a right triangle, and we know our Mr. Pythagoras, famous Pythagoras, he has given us a theorem to find this out. This distance is nothing but 4 square 16 plus 9, which is 25, and of course under root of 25 is 5. So this distance becomes 5, and that's the answer. Right? So that is the simple problem based on this concept, and it is being asked in the examination. So with that, we cover our chapter on boats and streams. Like I said, the questions are not difficult. You should be able to solve these questions if you have listened to this class carefully. The concept is slightly tricky, but if you keep your head straight, you will not make any mistake. In the next class, what I want to cover some problems which involve objects which have sizes. So the problems that we have discussed today and we have discussed in the past all involve objects which did not have size. The size of the object, size of the train, for example, size of the car was not given to us. We were only concerned by the distance moved by the object. In these problems, the size of the object which is moving, that the object itself becomes significant. So for example, if you notice in this train, it takes a finite amount for this train, a finite time for this train to cross this pole, right? The pole, we can consider it to not have any size, but the size of the train itself cannot be ignored, right? In many problems, they give you the size of the train, and in that case, you have to take that into account. Similarly, the time taken by these two trains, right? The trains did not cross instantaneously. It took them some time to cross each other. and that time, those times depend upon the length of the trains, and we'll discuss how to solve these problems in the very next class. Again, very important topic. You should definitely have a handle on this. So do subscribe to our channel. If you have questions, do not hesitate, put them in the comments below. I'll try to answer them as soon as possible. Thank you and good luck.